Note 13. You guys ready? What? Oh, it's the one that says note 13. I don't know, because sometimes over there in this table, they're all orange. All right, so here's the derivative formula, guys, or your instantaneous rate of change, which is just your derivative there. So all we're going to be doing is taking derivatives, but no longer are we using the derivative with respect to x. Now we're going to be taking derivatives with different letters. So here we go. Example 1, letter A. It says, find the rate of change of the area A of a circle with respect to its radius r. All right, so first and foremost, do we know the equation of the area of a circle? Yeah, so area of a circle is pi r squared. And sometimes if you were in algebra, they would write it like this, A of r, because it's dependent on r, is pi r squared. But you don't have to, you can just write it as A equals pi r squared. Now, I am taking the derivative, come on, Espinosa, focus, miss. I am taking the derivative with respect to what letter? R. So here we go. I'm going to take the derivative of A. So I'm going to write dA over dr. So the dr is what I'm taking the derivative with respect to. So if I take the derivative with respect to r, this is going to be what? 2. Yeah, you can say 2r. 2r pi or 2 pi r. See, you just, and that's it. I guess you can also say dr, but that's it. That makes sense or no? And you're done. That's the derivative. It says, find the rate of change of area of the circle with respect to its radius r. So dA dr is 2 pi r. Done. How do you feel? Okay. Evaluate the rate of change of A at r equals 5 and r equals 10. All right, so I'm going to write dA dr, evaluated at, that's a long line. It stands for evaluated at, r equals 5 equals, and I just write, what is it, 2 pi? 2 times pi times 5, so that is 10 pi. And then I write dA over dr at r equals 10 equals 2 pi times 10, so 20 pi. Nothing crazy, right? All right, and then it says if r is measured in inches and A is measured in square inches, what units would be appropriate for dA dr? Well, let's see, dA is in area and dr is in inches, so square inches per inch. So square inches per inch. Don't cancel out the units. Square inches per inch. Square inches of area per inch of radius. Don't cancel out the units. Cool or not cool? Okay, in case you're wondering, like, man, I have no idea what this is. I have no idea what this means. It's just a rate of change, guys. The top is like rate of change of area, and the bottom is like the change in radius. So the change in area over the change in radius. So square inches per inch. Yay? Okay. All right, let's keep going. All right, so here's where some of you are really good, I think. If I want, so what is this saying? This is saying that the derivative of position is velocity. Cool or not cool? Think about it. It makes sense, guys. Why is the derivative of position velocity? Well, remember, derivative means slope. And if you're finding a slope of a position time graph, your change in y over change in x is going to be meters per second or miles per hour, or a unit of change in distance divided by a unit of change in time. And distance divided by time is velocity. Does that make sense to you guys? Perfect. No, well, it's math. It's all math, not physics. It's math. Math is physics. All right. So the change, so look, this is all the instantaneous velocity is the derivative of the position function with respect to time. At time t, the velocity is, well, look, ds is change in position, dt is change in time. Change in position divided by change in time is velocity. So there it is. And then they tell you the speed is just the absolute value of velocity. That's all that means. And then it tells you here that I guess I should have put all three. Well, that doesn't matter. All right. The acceleration is the change in velocity divided by the change in time again. And that's what the slope of velocity is, right? If you have a velocity time graph and you get the slope of a velocity time graph, change of velocity divided by change in time. Well, change of velocity divided by change in time, that is acceleration. So the derivative of velocity is acceleration. What's the derivative of position? Velocity. What if I take the two derivatives from position? Acceleration, because the derivative of velocity is acceleration, which means you've taken the derivative of position twice. Does that make sense? Okay. No, you're good. All right. Real quick. 9.8 meters per second is the acceleration in metric. The acceleration in English is 32 feet per second. It's the same. It's just different units. Cool or not cool? Okay. All right. I think we're ready for some problems. Let's see if we can do it. All right. We never did example 1. Oh, that was example 1? Yeah, it was. Okay. All right, here we go. Example 2. A dynamite blast propels a heavy rock straight up with a launch velocity of 160 feet per second. It reaches a height of s equals 160t minus 16t squared feet after t seconds. Okay, before I continue, this equation, guys, did not come out of nowhere. Do you guys remember when you were in physics, he might have showed it to you like this. Change in x equals velocity initial times time plus 1/2 at squared. Do you guys remember that? All right, well, look, what's my initial velocity? 160, so that VI is 160. What's the acceleration due to gravity in feet per second? Feet per second, sorry. 32, right? But if I go down, it's negative 32. So if I put negative 32 for A, what's half of negative 32? Negative 16. OMG, look, there's that negative 16. This is that 160. So this came from your general physics equations. Cool or not cool? They're being nice and they're giving it to you here. So here we go. So it reaches a height of 160t minus 16t squared after feet seconds. It says, how high does the rock go? So I'm going to write this because I'm going to need it. Okay. I'm going to throw something up. Pretend this is a rock. Well, I guess anything can be a rock. When do I reach the highest point of this 10? When, okay, no, don't tell me the word slope. Use something else. No, use the word. Use when. Perfect. When this rock, well, it's not a rock. When this whiteout reaches its highest point, if I throw it, at the highest point, the velocity is 0, right? So that's what I'm going to do. I'm going to find where the velocity is 0, and I'm going to plug that sucker in to this equation to find how high this rock goes. Does that make sense or no? Yeah. All right, so here we go. Let's find our velocity. How do I find velocity? Take a what? A derivative of? Of what's that? Don't say that. Of my the position equation. So here's what you say. You write S prime equals V, because you're showing the evidence, which equals, you can also write ds dt. What's the derivative of 160t with respect to t? 160 minus what's the derivative of 16t squared with respect to t? 32t. I set this guy equal to what? 0. And now it turns into algebra. So I'm going to move the 32t to the right. So now I have 32t equals 160. And I'm going to divide that sucker by 32. So t equals, and I take my calculator. Do you guys have your calculators with you? Yeah, grab your calculators out, guys. Is it 5? And I need units. Seconds. All right, we're not done yet. That is just how long it takes for this to reach its high value. I got to plug in that 5 into my position formula. So here it is. S of 5 equals 160 times 5 minus 16 times 5 squared. So take your calculator and do that. 160 times 5, and I already forgot, minus squared. And there it is. There goes 400, and I need units. No, there's just position. Feet. It just goes 400 feet up in the air. Are we okay? Yep. All right.
No, that's so bad. I was just doing the Delta math, and I remember like doing exactly the same problem. but it wasn't like.
Well, you didn't take a derivative, but
Yeah,
it's similar.
That gives you like an x value. You're trying to like find like, oh, what was the slope?
What is the velocity and speed of the rock when it is 256 feet above the ground on the way up, on the way down? Okay, so they're asking two questions here. So they want to know when it's exactly 256 feet. So I already know my velocity equation. I need to figure out at what time I'm at 256. So use your position equation again. So you go 160t minus 16t squared and equal that sucker to 256. I'm going to move the 16t squared and the 160t to the right. So I have 0 equals, and I'm going to write the 16t squared first because it has the highest degree, minus 160t plus 256. I don't see any errors. I wanted to have the 16t squared positive. From there, I'm going to factor out a 16 because it looks like I can. T squared minus 10t, and how many times does 16 go into 256? 16 times? Plus 16. And then all that still equals 0. And I need to figure out, okay, ready for the factoring out of this? No, we're good. So what two numbers multiply to give you, there's a 1 in front of that t squared, right? So what two numbers give you, when you multiply, give you 16, but those same two numbers, when I add them, give me 10. And take your time. Negative. No, you're right.
Yeah, -2, -8.
Negative 2 and negative 8. T minus 2, t minus 8. Do you see how we did it? All right, so at these two values is when I'm at exactly 256. T. Can you tell which one's going on the way up and which one's going on the way down? Yeah, because it says they want to know the velocity on the way up and on the way down.
So I would imagine because you have gravity working against you, when you're going up, it would be the smaller one, and then down greater momentum.
Whoa.
Yeah, remember what the story is here, guys? Dynamite propels a rock. So if dynamite's propelling this rock, it reaches 256 up at 2 seconds, and then at 8 seconds, it's already going down. Cool or not cool? All right, so here we go. So by no surprise, when I plug in a 2, I better get a positive velocity. So V of 2 equals, and I just plug it into my velocity equation, 160 minus 32 times 2. So 160 minus 64, what's that? 90, 96, 96, and I need units. Feet per second. All right, now let's find it at 8. V of 8. 160 minus 32 times 8. And it's not going to be a shocker. It's going to be a negative number. Are you shocked that it's negative? No. 160 minus 32 times 8. Are you shocked that it's the same magnitude but just opposite? No. You're a little shocked? No, but are you shocked that they're the same?
Oh, like shock? Like, oh my god.
It's uniform. It's symmetric. All right, so, yeah. Okay, look, let's see. Look, I want you to make sure that you're in the game, guys. I hope you're not tired because then you're not in the game if you're tired. All right, think about it. You already found out how long it takes for it to reach the highest point. How long is this rock in the air total? It takes 5 seconds to reach the highest. From the ground, when it got shot up, 5 seconds. So it's 10 seconds. It takes 5 seconds to reach the highest, and it's going to take another 5 seconds for it to reach back to the ground level. So 10 seconds total. It's uniform. So at 2 seconds, it's going to be at the same magnitude, the speed. 250, 96 feet per second. And at 8 seconds, 2 seconds before it hits the ground, it's going to be at the same speed as well, 96 feet per second, but on the going down. The speed is the same, but the velocity is not. One's on the way up, the other one's on the way down.
It's like if you imagine a timeline and like put the two on each side and then
Yeah. See? All right. Letter C. What is the acceleration of the rock at any time t during its flight? Well, the only acceleration there is the acceleration due to gravity, and that better be what? Yeah, if you're in meters per second squared, but we're in feet per second, so Negative 32 feet per second per second. So feet per second squared. So if I take the derivative again of velocity, that better give me negative 32. So let's see if that's true. I'm going to zoom out so I can see my equation. So I'm going to write S prime prime equals V prime, which equals A, and which equals, so I go to my velocity equation right here, the 160 minus 32t, and I just take a derivative. Do I get negative 32? There it is. And then you just put your units, feet per second squared. Yay or nay? Okay. All right, you guys already answered this question, but you just don't know that you answered it. It says, when does the rock hit the ground? And 10 seconds. Now, let's prove it, though. I'm going to prove it with my position equation. So my position equation was 160t minus 16 squared. So let me zoom in. 160t minus 16t. Was it like that? Did I do it correctly? I'm going to equal this to 0 because that's where my position is. My position at the ground is 0. I'm going to factor out a 16. So I have 10t. Oh, you know what? Let me factor out a 16t. Put a t next to the 16. And I'm going to have 10 minus t. And I get two values. When is this 0? When t is 0? Well, yeah, that's when the blast off happens. And when t is 10. That's S for seconds. SEC. Yeah, everything's making sense. At 0, that's when the blast off happens. And 10 seconds, that's when it comes back to the ground. Cool or not cool? How do we feel? Okay. All right, let's go to the next one. Oh, you like my hashtags? I come up with them all by myself. Cardinal pride. A particle moves along a line so that its position at any time t greater than or equal to 0 is given by the function, and they give you a function, where S is measured in meters and t is measured in seconds. Okay, find the displacement of the particle during the first 2 seconds. Okay, displacement. S of 2 minus S of 0. I'm just finding my position at 2, finding your position at 0, and you're going to subtract those two values. I go to the side, and I go S of 2 equals 2 squared minus 4 times 2 plus 3. I'm not doing anything crazy. 4 minus 8 plus 3. 4 minus 8 is negative 4. Negative 4 plus 3 is negative 1. Did I do that correct? Okay. S of 0 will be easy. Plug in a 0. 0 squared minus 4 times 0 plus 3. S of 0 is just 3. Come back. S of 2 was negative 1. Minus S of 0 was 3. And 1 minus 3 is negative 4. And I put units. This is meters. So my displacement of the particle is negative 4 meters. So that means you're 4 meters to the left of where you started from, if you're in the x-axis. Yay or nay? Okay. Find the average velocity of the particle during the first 4 seconds. Average velocity is displacement divided by time. I already got my displacement up there, so I'm going to write velocity, AVG, equals, this is the average, it's not my instantaneous velocity, equals, I guess I'll write it, S of 2 minus S of 0 divided by 4. So that's a change in time. So negative 4 meters divided by 4 seconds, and you get negative 1 meter per second. Nothing crazy. That's just the average. Do we understand the difference between average and instantaneous? Okay, that's my average. Find the instantaneous velocity. How do I find instantaneous? I take a what? Derivative. So I get my equation. I'm going to say S prime equals V, which equals, what's the derivative of t squared with respect to t? 2t minus 4. So then I'm going to go V of 4, and I'll go slow so I can see you guys writing. And I'm just going to plug in a 4 wherever there's a t. 2 times 4 minus 4. 2 times 4 is 8. 8 minus 4 is 4. And then meters per second. You don't have to spell it out. You can just write m/s. I don't know why I spelled it out. Oh well. Sorry, not sorry. Hashtag. I said all that wrong. Hashtag sorry, not sorry. All right. Oh, you say it in the end? No, of course not. All right. Find the acceleration of the particle when t equals 4. How do I find acceleration, guys? Of which happens to be the what derivative of position? The second. So I'm going to write s prime prime, which equals v prime, which equals a, equals, what's the derivative of 2t minus 4? 2. And I need units. Meters per second per second. So meters per second squared. Cool or not cool? All right. Letter E. At what value of t does the particle change directions? Well, I need my velocity equation. What was my velocity equation again? Was it 2t minus 4? All right. If I were to graph this, and we're assuming t is greater than equal to 0, so minus 4, and then my velocity equation will look like this. Time, velocity. When do I change directions? When I cross the t-axis. Yes, you're right. You're right. The t looks like an x, so you're right. When I cross the t-axis, it's going to be at, I equal this to 0, and I just solve it, right? 2t equals 4, t equals half. I know that a lot of you can do this without showing the work, so for this, maybe I'm tempted to give you guys the credit. It changes velocity at half because velocity changes signs at half. Does that make sense? In case you're wondering, Chop, I have no idea what you're saying. Between t equals 0 and t equals half, I'm going to say that's half. Between t equals 0 and t equals half, velocity is negative. Oh, did I do that wrong? It's 2. Okay, yes. I was going to say, maybe I'm like crazy. No. I was wrong. Dang. And I'm going to upload this to YouTube. I already ruined it. I'll leave the error. It happens. Okay. Here we go. Sorry, guys. Miss, we're all human. All right. Sorry, guys. I am below the t-axis between 0 and 2. And then I'm above the t-axis greater than 2. What does that mean? Well, velocity is negative between 0 and 2. If velocity is negative between 0 and 2, you're moving to the left. If velocity is positive, you're moving to the right. This is one-dimensional motion. Does that make sense? So you just write a quick statement. You say velocity. Oh, I guess I should write the word particle first. Sorry, guys. Particle changes direction at t equals 2 seconds since velocity changes signs at t equals 2 seconds. Period. Full credit. How do we feel? All right, so you're done. That's today's notes. I don't think I put more. Did I put more? No. All right, so go to the activity. We're going to do some together. Let's do number 1 together, and then we'll do the rocket one. Or actually, we'll do number 3 as well. All right, number 1. Write the volume of a cube as a function of the side length s. Does everyone know how a cube looks like? There's my cube. Do you guys like my cube? I don't know why I got a D in art when I can draw cubes. All right, so there's my cube. Write the volume of a cube as a function of the side length s. Well, here's s, so that means volume of a cube equals s to the 3rd power. S times s times s will give me that volume. Yay or nay? Okay. Then the next one, letter B, says find the instantaneous rate of change of the volume with respect to a side length s. So that means dv ds. I'm taking the derivative of s cubed with respect to s. What's the derivative? Good job. Evaluate the rate of change of v at s equals 1. Oh, did I not take attendance? Hey, Ms. Corpus, is it attendance? Okay, I'll do it. Yeah, they're gonna fire me one day.
No, you're not. They would not fire you, Joe.
Yeah, I'm not taking attendance. You're hurting the bottom line. How do you think the school makes money?
How do you think it's going to do scores?
I don't think we make money with scores. You guys get the benefit of saving money. And you don't have to pay tuition for the Calculus 1 class. I didn't spend all that time in Cal 1 class. Right? Or no? Yeah.
I don't know.
No, like, you don't have to spend the money in the class, and you don't have to spend all that time in that class.
No, you don't have to take it because it's like now.
Oh, come on, guys. We're not in the same wavelength? Yeah, there's a disconnect today. Is it me?
It's like your sign or sign right now.
Okay, sorry guys. Let's all get on the same wavelength. Ready? Let's all jump together. Okay.
Can you jump off?
Yeah, I didn't even jump there. I just kind of just like did this motion. Okay.
What's the highest you can jump?
Miss, don't ask me those questions. All right. Evaluate the rate of change of v at s equals 1 and s equals 5. So here we go. So the rate of change, so I'm going to write dv ds at s equals 1 equals 3 times 1 squared, so I get 3. And then dv ds at s equals 5 equals 3 times 5 squared, which equals 75. If s is measured in inches and v is measured in cubic inches, what units would be appropriate for dv/ds? Cubic inches per inch. Do not cancel and call that square inches. That's not how this works. Because we're saying dv/ds. So cubic inches per inch. Are we still cool? Yeah. Okay. All right, so there it is. I'm going to let you guys do number 2 whenever we get a chance, but go to question number 3. I like this one. The figure to the right shows the what? Velocity. It labels the y-axis as velocity, so you don't have to put a v there, but that's fine. I did. Of a particle moving on a coordinate line. So you're either moving right or left. That's it. You're not, or up or down. Yeah, no, right or left. We're either moving right or left. That's it. You're on a coordinate line, right or left. When does the particle move forward, move backwards, speed up, slow down? Ooh, okay. Speed up and slow down, we might have to talk about that. But we know when we're moving forward. You're moving forward whenever the velocity is, and you're moving backward whenever the velocity is. All right, so maybe, should I color code these? Yes, okay. So I'm going to use sky blue for negative, which is almost the same color as that. And I'm going to use red for positive. All right, so I am moving positive, so moving forward, so I'm going to write move forward. I'm moving forward from 0 to 1. And again, I'm trying to think if I should use a parenthesis or a bracket. Because right at 1, I'm changing signs. Yeah, but you move forward or backwards in an interval. So bracket, comma, 5, comma, 7. Move backward from 1 to 5. Oh, and it looks like that's it. Backward. Backwards. I could be me, miss. I typed these notes out, so maybe I typed it wrong. All right. I think you guys are smart enough. Well, you guys are smart, but I think you guys are smart enough to know speed up and slow down by looking at the graph. but we need to know some definitions. Do you think I am speeding up or slowing down between 0 and 1? You're slowing down because the magnitude of that velocity is decreasing. Cool? And then between 1 and 2, you are speeding up. So the definition, because I want to make sure that you guys know, the definition for speeding up is if velocity and acceleration have same sign. And the definition for slowing down is velocity and acceleration have opposite signs. And I don't want you to be a robot. This is how you could be a robot, but I don't want you to be a robot, but let me tell you why. If velocity is positive, that means you're moving to the right. And acceleration is positive, that means the force for your acceleration is to the right as well. So you're going to be speeding up because your acceleration is positive, so you're increasing your velocity. Does that make sense? If your velocity is positive, that means you're moving to the right. But if your acceleration is negative, that means it's in the opposite direction. You're still moving to the right because velocity is negative, but the force is against you. So you're slowing down. Does that make sense? Yeah. If velocity is negative and your acceleration is negative, well, think about it. You're moving to the left, and the acceleration is the same direction as the direction you're moving, so you're going to be speeding up. If acceleration is negative but velocity is positive, then you're going to be slowing down because they're in opposite directions of forces. Cool or not cool? Okay. And that's exactly what's happening here, by the way. Chav, what do you mean velocity and acceleration are opposite signs? Well, look, between 0 and 1, velocity is positive because you're above the x-axis or the t-axis. But acceleration, remember, acceleration is just the derivative of velocity. What's the slope of that velocity curve? Positive or negative? So velocity is positive, but the slope is negative, which is acceleration, so you're slowing down. What about on the blue? Chav, what about the blue? Well, you're below the t-axis for velocity, so your velocity is negative, and your acceleration, is it still negative? It's negative, so the sign, everything works, so you're speeding up. Make sense? And then if the acceleration is 0, you're not speeding up or slowing down, you're just remaining steady. And then between 3 and 5, you're slowing down because the velocity is negative, you're below the t-axis, but your acceleration, what's the slope there? Positive, so your acceleration is positive, velocity negative, slope positive, well, acceleration positive, slowing down. Do you see that? Okay, so let's put this in here. I'm gonna put it in black because it's just neutral. Speed up on 0. Oh, nope. On, and you know what? Use parentheses for speed up. Speed up on 1 to 2, comma, and 5 to 6. And I think that's it. And then slow down on 0 to 1 and where is it? 6 to 7. Anywhere else? Oh, and yeah, I should put that one first if we're using union. 0 to 1, union 3 to 5, union 6 to 7. There. How do we feel? Nothing crazy? All right. When is the particle's acceleration positive? When is the acceleration positive? Between 5 and 6, but it also goes before 5 and 6. Acceleration. 3 all the way to 3, 6. When is it negative? I guess I'll put positive here. Negative. When is it negative? Between 0 and 2, and there's one more. 6 and 7. And where is it 0? 0, 2 to 3. Those are all interval notations. We're good? Okay. When does a particle move at its greatest speed? I don't know. It doesn't have numbers here. I guess at 0 at a moment and between 2 and 3 maybe. You're looking for the magnitude. When are you furthest away from the x-axis? Maybe that's a bad question. Here, I put it in parentheses. When velocity curve is furthest, quote unquote, away from t-axis. When does the particle move at its greatest speed? So it looks like at t equals 0, and then between 2 and 3. Yeah, not at 6, because at 0 it's higher than the 6 one. We're still okay? Okay. When does the particle stand still for more than an instant? Oh, I didn't even notice that. Look at this in purple.
Yeah, it's crazy.
Yeah. It stands still for more than an instant between 7 and... So then that means we didn't answer letter B completely. It's 0 between 2 and 3, union, and between 7 and 9, union. And I think that's it. Yep. All right, one more, and then we'll let you guys do the rest on your own. Look at question number 6. There's no. I gave this question to Wince a long time ago, so hopefully he showed it to you guys. But if not, no big deal. Because I thought this was a really good question for physics people. So, yeah, let's read it. When a model rocket is launched, the propellant burns for a few seconds, accelerating the rocket upward. After burnout, the rocket coasts upwards for a while and then begins to fall. A small explosive charge pops out a parachute shortly after the rocket starts downward. The parachute slows the rocket to keep it from breaking when it lands. The graph shows the velocity data data from the flight. Man, I can't read today. Okay, if you can read this graph, you can read any graph. Do you know what's happening with this graph? This is a what graph? The velocity time graph. So can you tell me, so I guess let's find out right here. How fast was the rocket climbing when the engine stopped? Okay, so I'm at ground level, then the engine starts burning. And it looks like, why do I have this giant, am I still going up after I pass this time? Yeah, you're still going up because the velocity is still positive. Yeah, so that means, so I'm still going up, but just not accelerating as fast. So that means that it stopped burning right at this time mark, which is at what time? 2 seconds. How fast was the rocket climbing when the engine stopped? The engine stopped at 2 seconds. I'm going to put that just for notes. Engine stopped at 2 seconds. They don't ask for that. I'm just putting that for you guys so you guys can know. So how fast was I going? It looks like I was going about, what did it look like to you? 190, and give me units. Feet per second. Oh, look at letter B. Dang. How many seconds did the engine burn? They should have asked that first. How many seconds did the engine burn? 2 seconds. You know what? Let me put it for good notes to switch. Switch for future notes. Sorry, guys. Future notes will be better because I'm going to make that edit. When did the rocket reach its highest point? I like it. When did I reach its highest point? Not at 2 seconds. At 8 seconds. I'm still going up, guys. Look at the velocity in feet per second. You're still going up. So you keep going up until how many seconds? 8 seconds. Because I got excited. What was its velocity at 8 seconds? 0 meters per second. Feet per second. I guess technically if it's 0, it doesn't matter. All right, now I'm falling after 8 seconds. Free fall. When did the parachute pop out? Yeah. Yeah, almost. 1, 2, 3, 4, 5. 2, 4. Yeah, 10. Like I'm gonna put the approximate symbol. Approximately 11 seconds. Put approximately because it's not exactly. How fast was the rocket falling then? It looks like almost a little faster than 90, like negative 90. Yeah. Negative 90-ish. I'm going to put approximate. 90 feet per second. That's the velocity If you say the speed is just 90 feet per second, approximately. How long did the rocket fall before the parachute opened? Oh, I love that question. When do you start to fall? Do you start to fall at 2 or at 8? At 8 seconds, you start to fall. So 8, 9, 10, 11. So approximately how many seconds? Approximately 3 seconds. When was the rocket's acceleration greatest? When was the acceleration constant? Well, when do I have the steepest tangent line? Right before the 2 second mark. Right before the 2 second mark. Right before the 2 second mark. When was the acceleration constant? Oh, well, the acceleration was constant between 2 seconds and 11. What do you think that slope is, by the way? You can. Acceleration is constant between 2 and approximately 11 seconds. All right. Is that it? Okay. That's it. But hold on. I want to know, take a guess. What do you think that slope is? What's the only force that's hitting that rocket? Just what? Just gravity. What's gravity?
9.8.
It's 9.8, but this is in feet.
32.
So I bet you that slope, if you were to try to calculate it, that slope is negative 32 feet per second squared. Isn't this cool? Look, this is just physics. You can ask. Look, there's.
I like this a lot.
Yeah.
More than-
Look, there's no derivatives in that whole thing. It's all just basic. Like, it is coming from a calculus book, not a physics book. And that's why I gave it to Wentz. And, like, if they can do this, they can do calculus. I don't see any other questions that are going to trip you up. But I am here, and I can help you. It's not due until Tuesday when we come back. But let's make sure we take care of business. So try to get as much as you can done today, guys. All right, we're done.
Something I probably should have been watching.